So, good morning once again to all of you. Let us continue with the chapter Chemical Bonding and Molecular Structure. This is chapter 4, and today the ninth day of myself transacting this lesson, 30th of August 2021. It's a Monday.
Yes, sir.
In the previous class, I had just introduced the molecular orbital theory, nothing more than that. And I had told that in molecular orbital theory, atomic orbitals, equal number of atomic orbitals combine. They linearly combine to form molecular orbitals, equal number of molecular orbitals as well. Now today, if you look at this slide over here, when bonding molecular orbitals are formed, that means there is lowering of energy. Okay, and that lowering of energy, it is called stabilization energy. It is called stabilization. This is a very important slide. The lowering of the energy of bonding molecular orbital than the combining atomic orbital. If this is the combining atomic orbitals, okay, so 1s over here 1s. So the bonding molecular orbital, it is lower in energy. It is lower in energy. So this lowering of energy, it is called stabilization energy. Okay, and similarly, increase in energy of the anti-bonding molecular orbitals is called destabilization energy. For example, when anti-bonding molecular orbitals are formed this way, this is sigma star 1s, that time there is a rise in energy, increase in energy. So this increase in energy, it is called destabilization energy. Okay, now moving further to the next slide, formation of molecular orbitals by linear combination of atomic orbital method. Now here the first point, if you see, when the atomic orbitals overlap in phase, both having positive amplitude. When the atomic orbitals overlap in phase, both having positive amplitude, like this. If this is atomic orbital 1, another atomic orbital, okay. If they overlap in this way, if there is overlap happening this way, positive over positive, that time the molecular orbitals formed are called sigma molecular orbitals. So when the orbitals overlap in phase, both having positive amplitude, okay, along the internuclear axis, the molecular orbitals formed are therefore called sigma molecular orbitals. Otherwise, otherwise, when the atomic orbitals overlap not in phase, which means one having a positive amplitude and the other one having a negative amplitude, sidewise overlap. This is sidewise overlap. Okay, the molecular orbitals formed are called pi orbitals. Pi molecular orbitals. Okay, so this you must remember, keep in mind. Okay, now after that, look at this diagram. It will help you understand this linear combination of atomic orbitals. The first part over here on the top, wave functions for sigma 1s orbital, plus here also plus 1s orbital. Okay, now these are for hydrogen atoms. Okay, and when they are combining, the plus of one is overlapping with the plus of other, so this one is a constructive interference which results in a bonding molecular orbital, which is called, in terms of wave functions, it is called bonding probability density for electrons. You'll find electrons in the regions over here. Now, the other diagram over here just below, it is for wave functions for sigma star 1s antibonding. The plus and minus, they overlap, which results in higher energy. The energy is very high. So that time it is called destructive interference. It is called destructive interference, and in this situation, the molecular orbital which is formed is antibonding molecular orbital. In terms of this language, it is called antibonding probability density. Okay, so electrons are not found over here. Electrons are not found in the nodal region. They are absent. That's why it is an empty space which is given a name. node, whereas electrons are found behind. Electrons are found behind over here. Okay, so that is anti-bonding molecular orbital. So this diagram should help you understand constructive interference resulting in the formation of bonding molecular orbitals, as well as destructive interference resulting in the formation of anti-bonding molecular orbitals. Moving further, molecular orbitals from s orbitals. If you look at this slide over here on your screen, one s orbital, another s orbital, they combine to form atomic orbital. This combine, and then if there is a subtraction, means destructive interference, then it forms anti-bonding molecular orbitals. Otherwise, if there is addition of the wave functions, constructive interference, then it results in the formation of bonding molecular orbitals sigma s. This is sigma star 1s. So whenever there is anti-bonding, remember the star is put over there, sigma star 1s, and so on. Now moving to the next slide, you can see again similarly molecular orbitals from p orbitals, px, py, or pz. Okay, we'll talk about px and py first. Okay, now when a 2px atomic orbital combines, overlaps with the 2p, another 2px atomic orbital, then there is head-on overlap. Okay, of two atoms. There is energy over here mentioned over here. So it is happening in two ways over here. Over here 2py, 2py. Over here 2pz, 2pz. 2pz, 2pz. It is sidewise overlap. Sidewise. That's why it is forming pi bonding molecular orbitals. Okay, sidewise overlap. Pi molecular orbitals. Okay. Now one is anti-bonding, one is bonding here also. Now here again same thing. 2py, 2py. It is again sidewise overlap, so it is forming pi 2p. It is here. It is forming pi star 2p. Okay. Only x orbitals. Only x orbitals. Only x orbital they form sigma bonding and sigma star anti-bonding molecular orbitals. The remaining two, that is 2py and 2pz, they overlap always sideways to form pi bonding and pi anti-bonding molecular orbitals. So this is how formation of molecular orbitals from p orbitals happen. Now let us compare these two sigma molecular orbitals and pi molecular orbitals one by one. The sigma molecular orbital, it is formed by head-to-head overlap of atomic orbitals. Head-to-head overlap, this way. Okay. Whereas the pi molecular orbital, it is formed by the sidewise, either this way or this way. Sidewise overlap. Okay, along the endonuclear axis. That is in the case of py or pz atomic orbitals. Okay. Then number two, the sigma molecular orbital overlapping is along internuclear axis. But in the case of pi molecular orbital, the overlap is perpendicular to the internuclear axis. It is perpendicular. Okay. Then number three, under sigma molecular orbital, as a result of this, strong bond is formed. Whenever there is a formation of sigma bond, the bond which is formed, it is really a strong one. Number three, in the case of pi molecular orbital, as a result of this, pi bonds are weak, so weak bond is formed. Number four, under sigma molecular orbital, this orbital is symmetrical to rotation about the line joining the two nuclei. It is symmetrical. It can rotate. It can rotate. If they combine, it can rotate. You can rotate it either this way or it can rotate this way also. But in the case of pi molecular orbital, this orbital is not symmetrical to rotation because it is perpendicular. It is perpendicular to the nuclear axis. That's why it's difficult rotation. It is not symmetrical to rotation about the line joining the two nuclei. So this makes things difficult, and because of this impossibility of what you call rotation, it is weak bonds. Number five, under sigma molecular orbital, the region of overlap, it is greater. Region of overlap is greater, but in the case of pi molecular orbital, the region of overlap is lesser. Okay, so these are some basic differences between sigma and pi molecular orbitals. Okay, now the next thing is quite important. Next thing which you're going to learn is quite important. Have a look on the screen over there. Just a second. Okay. You can see on your screen there are some energies, relative orbital energies. Okay, this is one part. Okay, this is one part, this is the other part. You must learn this. You must learn this order. You must learn this order. Okay, how will you learn? 1s sigma star 1s, 2s sigma star 2s, 2py sigma 2px, pi 2py sigma star 2px. This way you have to learn this order. I'll write in a much better form in the other slide also. For molecules like oxygen, fluorine and neon, the order is slightly different. This has gone up and this one has come down. Okay, in this case. Okay, so here you can see the sigma 2px orbital has come down. So the order is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2px, pi 2py, pi star 2py, then sigma star 2px, and so on. Okay, so this is the relative order of energies of the molecular orbitals. You have to learn this for lithium, beryllium, boron, carbon, and hydrogen molecules. You remember this order, and only for oxygen, fluorine, and neon you remember this order. Okay, okay. Now here, if you see the orbital energies, the relative orbital energies for oxygen, fluorine and neon, it is slightly different from the first one because this, if you look at them very carefully, oxygen, fluorine electronegative, neon molecule, neon atoms are stable, having 8 electrons in the valence shell. So because of this, these two anomalies over here, their relative orbital energy is slightly different from those of lithium molecule or beryllium molecule or boron or carbon or nitrogen molecules. Okay, so now using this relative order of energies of molecular orbitals, this is what you'll have to learn for lithium or boron or carbon or nitrogen. First this one. Okay, now see sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2px, pi 2py, pi star 2py, sigma star 2px, pi 2pz, pi star 2pz. Now using this relative order of energies of the molecular orbitals, we are going to learn how to draw the molecular orbital diagrams and electronic configuration of some homonuclear diatomic molecules and molecular ions. So for this, I'm giving you some time. Have a look at this very carefully. Okay, and in the beginning you have to write it several times, and after some time you get habituated and it enters your mind, and then you can write this order easily. Now in the beginning we'll come back to this slide again and again. Okay, but just now let me show you one example. Okay, now let's take the first example, that is formation of hydrogen molecule, molecular orbital. Okay, now during the formation of hydrogen molecule, we know that there are two hydrogen atoms required. There are two hydrogen atoms required. So I'll write down over here one hydrogen atom. Okay, over here I'll write down another hydrogen atom. Okay, this hydrogen atom, this I'll write over here atomic orbital. I'll write atomic orbital. Here also I'll write atomic orbital. Okay, now slightly above this, I'll draw the what do you call atomic orbitals this way. Just a line this way. And below this I'll write 1s atomic orbital, because the electronic configuration of hydrogen is 1s. So I'll write 1s containing one electron each, containing one electron each. Okay, so this is one atomic orbital, this is another atomic orbital. Now they have to combine by the linear combination of atomic orbital method. So I will make a dotted line over here. Dotted line over here. Here also I'll make a dotted line. Okay. Then I will draw a line and then make two molecular orbitals like this. Make two molecular orbitals like this. Okay. This lower one, it is a molecular, it's a bonding molecular orbital. So I will name this as sigma 1s, sigma 1s, and the higher than that is what? It is sigma star 1s. Okay, so I'll name this as sigma star 1s. Now check the total number of electrons. The total number of electron is one over here, another one over here. So both these electrons will follow the Hund's rule, the above principle, okay, Pauli's exclusion principle, and they will fill up the lower molecular orbital this way. So the electrons are finished, okay. The electrons are over now. So both the electrons they are filling over here, okay, they are filling over here. Now this is the molecular orbital diagram for hydrogen molecule. This hydrogen molecule, okay, molecular orbital diagram. This is how we represent sigma 1s. It has two electrons. The bonding, both are bonding electrons. Now, after getting this, it is very important for us to calculate, to find out the bond order. Bond order, there is a formula, half Nb minus Na. Now, I'll tell you what is Nb and Na. Nb means bonding electrons, number of bonding electrons, and Na means number of anti-bonding electrons. Okay, so we apply this formula and get the bond order. So bond order, if I apply the formula, half Nb, number of bonding electron is 2, okay, minus Na, number of bond electron over here, it is 0, anti-bonding is 0, so half into 2 minus 0, it becomes 1. So the bond order for hydrogen molecule is coming to be 1. What does this mean? What does this mean? Tell me. The bond order of hydrogen molecule is coming to be 1. This bond order coming value which has come to 1 means it is a single bond. Bond order 1 means it is a single bond. It is a single bond. And moreover, for bond order 1, the bond is positive. It makes the molecule stable. It makes the molecule stable. And moreover, there are no unpaired electrons. This is paired. Okay, so since there are no unpaired electrons, everything is paired. Therefore, hydrogen molecule, it is what? It is diamagnetic in nature. It is diamagnetic in nature. Hydrogen molecule is what? Diamagnetic in nature, which means it is not affected. It is not affected by magnetic fields. So these three things we have to work out after the diagram and write down after the diagram. First, calculate bond order. Once you get the bond order, if the bond order is 1, it is a single bond. If the bond order is 2, it is a double bond. If the bond order is 3, it is a triple bond. And if it is a single bond, double bond, triple bond, definitely the molecule will be stable. Higher the bond order, the stability will increase. After that, come back and look at the diagram carefully. If all the molecular orbitals contain pair electrons, which is diamagnetic. But if there is any unpaired electrons, that time it will become paramagnetic. Okay, so this was the first example for drawing of the molecular orbitals for the formation of hydrogen molecule. Now the next one, what I would like to show you is the second example, that is number 2. That is number 2. I am writing down over here formation of molecular cation. Formation of molecular cation, hydrogen molecular cation, H2 plus. Now H2 plus. So I'll draw an arrow like this, which shows increasing energy, and over here hydrogen H plus ion. Okay, because we need one positive charge. This is atomic orbital of hydrogen ion. This side I will take hydrogen atom. Okay, so this is also atomic orbital. Okay, then just above this, slightly above this, I'll make the atomic orbital 1s, over here also 1s. The hydrogen ion doesn't have any electron, so no electron. So there is no electron over here. But in the case of hydrogen atom, there is one electron. Okay, now I'll draw dotted lines like this over here. Dotted lines. Here also dotted lines. Now I will combine the atomic orbitals and make molecular orbitals this way. Okay, this way. This way. So this one becomes sigma 1s bonding molecular orbital. This becomes sigma star 1s antibonding molecular orbitals formed by head-on overlap. Now, total number of electron is only one. So this one electron just comes very happily and enters the sigma 1s molecular orbital. So the diagram is complete. Now, this hydrogen molecular cation, now it can be represented this way. H2 plus, okay, colon over here, sigma 1s containing one electron only. And now immediately we'll calculate the bond order. Bond order is half NB minus Na. So if you calculate the bond order, it becomes half NB, number of bonding electrons. It is only 1. So 1 minus 0. So I am getting the value of bond order is simply half. Now the value of bond order half means it is supposed to be a half bond, not a full bond. It is a half bond. So bond order, just calculate. It is coming half. Yes. Now on the basis of the value of the bond order, we can say the bond is unstable. The bond is unstable. The bond is unstable, and the bond length is longer. The bond length is longer, and since there is an unpaired electron in the bonding molecular orbital sigma 1s, so this hydrogen molecular cation, it is paramagnetic. It is paramagnetic. It is paramagnetic, which means it will be affected by magnetic fields. If magnetic fields are brought closer to this hydrogen molecular cation, which is already an unstable molecule, it will show paramagnetic behavior. So this is the second example for the drawing of molecular orbital for the formation of molecular hydrogen cation. Is that clear, my dear boys? Is that clear? Okay, so let us go
Yes,
to,
sir.
let us move to one more example. We will do examples, and from the examples we learn how to draw the molecular orbitals. The third one on the screen, the next one, it is called hydrogen molecular orbital for hydrogen molecular anion, anion, hydrogen molecular anion. Okay, so I'll write anion is negative charge, so H2 minus, like this, H2 minus. Again, I will draw the energy arrow. Okay, here I will take hydrogen atomic orbital of the anion. Okay, let's take this as the anion. Here I'll take hydrogen atomic orbital of the atom. Okay, anion means it has one extra electron, so here I'll put the orbital, atomic orbital, small lines like this over here. This will be 1s, this will also be 1s, but since this one is an anion, hydride ion, so this will contain 2 electrons, and this atom will contain 1 electron. Now I'll draw dotted lines over here, here also dotted lines to demarcate the atomic orbitals from the molecular orbital. The center one is what? The center one is the molecular orbitals. Okay, now I'll draw the line and make the molecular orbital like this, like this. Okay, so this one becomes sigma 1s. This one becomes sigma star 1s. Now total number of electron is 2 plus 1, that is 3. So I'll put the electron this way. 1, 2, and remaining 1 goes up, because we know an orbital can accommodate maximum of 2 electrons. Okay, so this is the molecular orbital diagram for hydrogen molecular anion. So this is how we write it. Hydrogen molecular anion, we write the electronic configuration this way. Sigma 1s whole square, again sigma star, because sigma star, the antibonding also contains electrons, sigma star 1s 1 electron. Okay, after that we calculate the bond order. The formula is half. Yes, hello. Every time the first thing you have to do is calculate the bond order. So bond order is half Nb minus Na. So when you do this, we get half Nb. Number of bonding electron is 2, minus number of anti-bonding electron is 1. So 1 over here. So 2 minus 1 is 1. So I'm getting over here again half. So bond order is again coming to how much? It is coming to half, which means it is an unstable. It is an unstable molecule. The stability is less. It is bond order is half, means the stability is less. And moreover, after the stability, after the bond order and the stability, then we look at the any unpaired electrons. There is one unpaired electron in the sigma star 1s orbital. So because of the presence of the unpaired electron in the sigma star 1s orbital, this hydrogen molecular anion is again, it is again paramagnetic. It is again paramagnetic. It is again paramagnetic in nature. Am I clear? Am I clear, my dear boys?
Sir.
Okay, so please go through this. Please go through these diagrams and explanations exhaustively with a lot of details. Okay, and then you can refer to your textbooks as well for the drawing of the molecular orbital diagrams. Okay, and this will make your picture clear. But you must remember, this increasing order of energy molecular orbitals. This you must remember. Now, moving to the next slide, I'll do some more examples to make this idea very clear. Number 4. Number 4, I am taking the example of helium. Helium molecule. Helium molecule. The formula is He2. Now we know helium. Helium, the electronic configuration, we know it is 1s2. Okay, helium atom. So I'll need 2 helium atoms. So I'll first draw the energy arrow. Energy arrow on the left hand side of the page, and then I'll write over here helium atomic orbital. Here also I'll write down another one, helium atomic orbital, and then I'll draw dash over here, another dash over here for the atomic orbitals. 1s, 1s atomic orbital for helium, each of the helium atoms. Now we know there are 2 electrons present in an atom of helium in the what you call orbital, s orbital. So I'll put 2 electrons here, another 2 electrons over here. Okay, then I will draw dotted lines to demarcate the atomic orbital from the molecular orbital this way. Okay, then I will mix them up and make molecular orbitals this way, okay, this way. Okay, then this one is sigma 1s molecular orbital. The center one is, this is molecular orbitals. Okay, then this one is sigma star 1s. Now look at the total number of electrons given by both the helium atoms. Total is 4. 2 over here, 2 over here, 4 of them. So this will fill up this way: 1, 2, 3, and 4. Okay, so this is the molecular orbital diagram for helium molecule. Now to write down the electronic configuration according to MOT, this is how we write it: He2 dot dot, and then sigma, open the bracket, sigma 1s, 2 electrons, sigma star 1s, another 2 electrons. So this is the electronic configuration according to molecular orbital theory for helium molecule. After that, I'll calculate the bond order. bond order is equal to half Nb, number of bonding electrons minus number of anti-bonding electrons. So here half Nb value is 2, Na value is also 2. So if I simplify this, I am getting bond order as 0. Bond order is 0. A remarkable calculation. So the bond order for helium, it is coming 0, which means no bond. There is no bond. No bond that exists. That exists. That means helium molecule is not possible. Helium molecule is not possible. Helium molecule is not possible. So if the bond is not possible, then there is no question of magnetic behavior. So we have to write down at the end, helium molecule cannot exist. Helium molecule cannot exist. There is no question of existence of the helium molecule. So this is how you have to draw and show the possibility of existence, the bond formation, okay, or the bond strength after drawing the molecular orbital diagrams and writing down their electronic configurations, what you call probability. Okay, now let us move to the next example for the formation of molecular orbital diagram number 5, the fifth one. Number 5, it is called helium molecule ion. Helium molecule ion. Helium molecule ion. The formula is He2. Molecule ion means one charge, one positive charge. Okay. Now we need two helium atoms. Okay, and one has got less one electron. Okay, so again, what I will do is I'll draw the energy arrow at the side, left hand side. Okay, and then helium ion I will take He plus atomic orbital, and this side helium atom atomic orbital. Okay, this helium ion, it is short of one electron, so I will draw the atomic orbitals like this. This is 1s, this is also 1s. This atomic orbital, it is short of one electron. Helium atom is supposed to have two electrons, but this is ion. He plus means it is short of one, so one electron only. But this helium atom will have two electrons. And now after this, I will draw dotted lines to demarcate the atomic orbital from the molecular orbital. This way, in the center, I will write over here molecular orbitals, and then now I'll mix the atomic orbitals and make the molecular orbital this way. Okay, so this one is sigma 1s, that is bonding molecular orbital. This one is anti-bonding molecular orbital 1s. Now total number of electron is 1 plus 2, that is 3. It is 3. So I'll fill the vertical orbital this way. Molecular orbital this 1, 2, and 1 goes up over here. Okay, so this is the molecular orbital diagram for helium molecular ion, and the electronic configuration according to MOT becomes like this. He2 plus will write like this: sigma 1s containing 2 electrons and sigma star 1s containing 1 electrons. And after that we will calculate the bond order. We will calculate the bond order is equal to half Nb minus Na, and we know Nb it is 2 electrons, Na it is 1 electrons. Okay, so 2 minus 1 is 1, 1 by 2, 1 divided by half is half only. So the bond order over here, it is coming to half, which means it is an unstable molecule. It is an unstable molecule. And moreover, after the stability, you look at the orbitals. This orbital contains one electron singly occupying the orbital. So helium molecular cation, it is supposed to be paramagnetic. It is supposed to be paramagnetic in nature. Am I clear? It is supposed to be paramagnetic in nature, somewhat similar to the hydrogen molecular cation, somewhat similar to this. Okay, so this is the fifth example. for the drawing of molecular orbital diagrams. So I have completed 5 of them. There is some time. Let me complete one more. Okay, one more. The sixth one, number 6. I'm writing down. Yes. Anybody got any question? Okay. Number 6. Now, number 6. I'm taking the example of lithium. Lithium molecule. Lithium molecule Li2. Okay, lithium. We know lithium atom, hydrogen, helium, lithium. Atomic number is 3. Atomic number is 3. Electronic configuration is 1s2, 2s1. Okay, an atom of lithium has electronic configuration 1s2, 2s1. So here, now we are using two orbitals. One is 1s, another one is 2s. Okay, so, and we're using two lithium atoms. So let us draw the energy arrow at the left hand side, and then take two lithium atoms, Li over here, another Li over here. This is atomic orbital. This is also lithium atomic orbital. Now here I'll make 1s, here also I'll make 1s. Then we need one more, 2s also we need. So I'll make 2s, 2s, here I'll make 2s. Now I'll combine, I'll make dotted lines over here to demarcate the atomic orbital from the molecular orbital. Okay, this is the molecular orbital in the center. Now I'll combine them. I'll allow their combination. So I'll make this way, this way, this way. This one is sigma 1s. Okay, this one becomes sigma star 1s. Here again the 2s will also combine. Okay, this way. This becomes sigma 2s now. Sigma 2s. And this becomes sigma star 2s. See, look at the order. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Okay. Now let us put the electrons in the atomic orbitals. 1s orbital has 2 electrons. 1, 2. This also has 2 for one lithium, the first lithium atom. And the 2s has 1 electron. So I'll put one over here, another one over here. So now count the total number of electrons. 2 plus 2, 4, 4, 5, and one more is 6. There are 6 electrons altogether. But we'll fill the orbitals in the correct order. Total 4 means 1, 2, 3, 4. This is 2 means 2 will come over here. Okay. So that's done. So this is how we draw the diagram for lithium molecule. Now to write down the electronic configuration according to molecular orbital theory, for lithium molecule we have this way. We write this way. Lithium molecule we write this way. Li2 sigma 1s 2 electrons, then sigma star 1s another 2 electrons. After that sigma 2s 2 electrons. That's it. Okay, these two inner shells can be written as kk. You can write it as kk. Kk denotes what? The closed shell. This is a closed shell. This one is a closed shell. Okay, so we write instead of this thing later on slowly for higher atomic number molecules you can just write kk, okay, or ll depending upon which molecule we are preparing. Now we can work out the bond order. Bond order is equal to half Nb minus Na. So over here for lithium molecule, the number of bonding electrons, just take this one only, not for the closed shell. So half Nb becomes 2 minus anti-bonding is 0, so it will come 1. So the bond order is coming to 1. That means it is a single bond. It is a single bond between the lithium molecule. And moreover, after the single bond, if you see very carefully, there are no electrons, unpaired electrons. All are paired electrons. This is paired electron, this is also paired electron, this is also paired electron. So this lithium molecule will be diamagnetic in nature. It will be diamagnetic. It will be diamagnetic in nature. Okay, it will be diamagnetic in nature. So I have drawn 6 examples for molecular orbital diagrams. I would like to stop my class here only because it's already time up. So I'll continue with the remaining construction or drawing of molecular orbital diagrams tomorrow, and most probably tomorrow I shall complete this chapter. Okay, now just hang on over there because I need to record your attendance. Okay, I'll just record your attendance quickly, and then you can go and join the other class. Okay. Okay, the attendance list is downloaded. Thank you so much, boys. Have a nice day.
Thank you, sir.
Thank you. Thank you.